Alright, we got a pretty fun problem, so let's get to it. The statement reads, suppose you have two infinite straight line charges, lambda, a distance d apart, moving along at a constant speed v. How great would v have to be in order for the magnetic attraction to balance the electric repulsion? Work out the actual number. Is this a reasonable sort of speed? Let's draw this out real quick. Two parallel lines, both charged lambda with speed v in the same direction, separated by distance d. All right, pretty similar to how we derived the magnetic force. Speaking of magnetic force, the magnetic force per unit length is F equal mu naught over 2 pi times I1, I2 over d, where I is lambda v, since charge or current is moving charge. And then the electric field of a wire, which we found in chapter 2, or you can just redo it with the Gaussian surface, is 1 over 2 pi epsilon naught lambda over s. All right, so the magnetic attraction per unit length is Fm equal mu naught over 2 pi lambda v, since they're both the same, over d, leaving us with mu naught over 2 pi lambda squared v squared divided by d. Now, the electric repulsion per unit length is F equal QE, but here we know what V or E is, and Q is just lambda, so we put the two together and we get that FE is equal to 1 over 2 pi epsilon naught lambda squared divided by D. Now they balance when Fm equals Fe, and we see that when we set them equal to one another, a lot of things cancel. 2 pi on both sides, lambda squared over d on both sides, yields mu naught v squared equal 1 over epsilon. Solving for v squared, we get 1 over mu naught times epsilon naught. Again, taking the square root of both sides, we get v is equal to 1 over the square root of epsilon naught mu naught. This should look familiar. Plug it in their values, and we get v equal 1 over the square root of 8.8 times 10 to the negative 12 times 4 pi times 10 to the negative 7, which equal 3.0 times 10 to the 8 meters per second. Ring a bell yet? This is precisely the speed of light. So in fact, you could never get the wires going fast enough. The electric force will always dominate.